Hi everyone, Nick Russo here, and welcome back to the BGP Multi-homing series. Much like the previous video, suppose AS65000 is using a full mesh of iBGP between all routers and wants to use both R4 and R5 for egress routing towards R6. However, one link is twice as fast as the other, and ideally, AS65000 can use these links in proportion to their link bandwidths, resulting in a 2-to-1 ratio. The core design still uses a full mesh of iBGP peers, but will need to enable some additional features to correctly configure unequal cost multipath, or UCMP. We'll use IPv4 for this example, as Cisco iOS does not appear to support UCMP for IPv6 destinations. R6 advertises 192.0.2.6/32 towards R4 and R6 with no attributes or communities. R4 and R5 prefer these eBGP paths just like last time, but when they advertise them to their iBGP peers, they add a new community. BGP communities are like route tags that can signal arbitrary information, and in this case, the extended community of DMZ Link Bandwidth is applied. This allows each BGP route to carry the inter-AS link bandwidth in band. When R3 and other iBGP speakers receive these routes, they install both routes just like in ECMP because this community does not impact BGP best path. It does, however, influence the RIB and FIB share ratios, allowing R3 to send twice as much traffic to R4 when compared to R5 because it has a faster connection to R6. Before we jump into the demo, you should know about my Cisco Advanced Routing courses at Pluralsight. Rather than teach various topics in isolation, I developed unique, large-scale topologies to illustrate how the technologies interact. If you need to brush up on your routing protocols, tunneling techniques, or management services, click the link in the video description to get started. Now, onto the demo. Starting on R4, I've displayed the BGP configuration. To enable unequal cost multipath, the egress PEs must be able to signal their link bandwidth. We enable the transmission of extended communities from R4 and R5 to their iBGP peers. Thanks to our peer policy template, we can enable this for all IPv4 and IPv6 peers using a single command. In Cisco iOS, communities are not advertised by default, but other network OSs may behave differently. Cisco iOS XR, for example, advertises communities to iBGP peers by default, but not eBGP peers. Be sure to check your product's documentation. Next, both R4 and R5 must enable DMZ Link Bandwidth on the eBGP peerings for which they want to signal link bandwidth. I've enabled it for both the IPv4 and IPv6 peers, but we'll focus on IPv4 in this demo. Let's check the BGP table for 192.0.2.6/32, R6's loopback prefix, from R4's perspective. We see two routes here. One route is learned from R6 via eBGP and has a link bandwidth of 250,000 kilobytes, or 2 gigabits per second. This is R4's best path because eBGP is preferred over iBGP, all else equal. The other route is iBGP learned from R5 and has a bandwidth of 125,000 kilobytes, or 1 gigabits per second. This is R5's best path, and just like R4's best path, is advertised to the remaining AS65000 routers in the iBGP mesh. Before moving on, let's quickly review the PE to CE interface configuration on R4. When DMZ link bandwidth is enabled on a given eBGP peer, the egress interface towards that peer will have its bandwidth evaluated. Per the diagram, this interface should have a bandwidth of 2 gigabits per second, which it does. R5 has a value of 1 gigabits per second configured on its PE to CE interface as well. Let's head to R3 next. I've displayed the BGP configuration and scrolled to the bottom. Multipath is still enabled for iBGP routes with a maximum of 2, which allows BGP to offer up to 2 routes to the RIB for installation. However, I've also enabled link bandwidth support, which tells BGP to examine the extended communities applied by R4 and R5. Let's check the BGP table for R6's IPv4 loopback from R3's perspective. R3 learns both routes via iBGP, and both are used for multipath, just like in the previous video. Notice that each route has a DMZ Link Bandwidth community, indicating that both R4 and R5 correctly advertised them. Next, let's check the routing table for this destination to ensure both routes are installed. At a glance, we see two entries here, one from 10.0.0.4 and one from 10.0.0.5, which are the IPv4 loopbacks on R4 and R5 respectively. That's a good sign, but our goal is unequal cost multipath. Fortunately, we also see the traffic share count ratio of 2:1 with a preference for R4. This is correct given our link bandwidths of 2 gigabits per second and 1 gigabits per second. Now, when you adjust those link bandwidths in the future, BGP will automatically load share in proportion to those bandwidths. That means 2 flows via R4 for every 1 flow via R5.